This video, we're going to be taking a look at higher order derivatives. So for example, just differentiating again and again and again. That's what we mean. Let's try one example first. F of x is equal to 5x squared plus 9x minus 2. If we go ahead and differentiate that, f dash of x equals 10x plus 9. If we go further, we know that f double dash of x is just 10. This essentially means that the rate of change with respect to a tangent of the gradient at any point is 10. That's what that means here. But let's try something more tricky. Let's just try a simple trigonometric problem where we have g of x equal to sine 2x cubed minus 9x. Oh, that's a terrible 9. You can go ahead and try to find the second and first derivative of this function. To find the first derivative, you need to recall that first we can keep the function as it is, but we know that sine differentiates into cos. And we need to remember that the inside bracket also needs to be differentiated and multiply. So in the end, we should get 6x squared minus 9 cos 2x cubed minus 9x. But what about g double dash of x? You can pause the video and try for yourself. Coming back to the problem, let's approach it together. So we know that this is g of x, and g dash of x was stated to be 6x squared cos 2x cubed minus 9x. Here we can see that we do have two components. We have this bracket and we have this trigonometric function. Let's call this u. Let's call this v. Oh, sorry about that. Oh, that's a terrible v. There we go, u and v. We can use the product rule here to differentiate further. Essentially what the product rule is if we have a function uv and we want to differentiate it, we can express it simply as u, the differentiated version of u prime, v multiplied by v, plus u, v prime. So we're going to be applying this formula above. So d squared y over dx squared is equal to g double dash prime of x. That's going to be equal to u prime, which would just be 12x from 6x squared. Differentiating minus 9 just leaves us with 0. multiplied by the rest of the function v plus the regular form of u, and this time multiplied by the differentiated version of v. In this case, cos, we know cos differentiates into minus sign. And I seem to have run out of space. Let me just write it below then. So we have our u and our v prime. Our v prime is a minus sign of the function inside, multiplied the differentiation, the first derivative of the inside function, which will just give us 6x squared minus 9, all in big brackets. So our final clean expression for the second derivative here (12x cos 2x cubed minus 9x minus 6x squared minus 9 squared, because there were two of them, so we can just raise that to the power of 2 to make it simpler, times by sine 2x cubed minus 9x. This sign here, you're probably wondering why is it positive? Well, it really isn't, because all we did was just move the negative to the front here. So when adding on the second part of our final answer, the positive sign, the plus symbol, just turns into a minus sign, negative symbol. Let's try a couple more problems. Now we're going to run through them a little faster because we've got the hang of this. So first we're going to say we have a function z. Z of x is log of x of 7 minus x cubed. You can try and pause the video and find out the first derivative, but we're going to jump straight in. For a log, first you need to differentiate the inside bracket. So that will just give us minus 3x squared from the x cubed over here. But we also need to multiply it by 1 over whatever is in the inside bracket, 7 minus x cubed. And that's your first answer. But what if you want to find the second derivative? You can pause the video and try to have a go using the quotient rule to differentiate. We can try this problem together. So first, we can say this is u and this is v. Let's differentiate u first. As according to the quotient rule, we have minus 6x, v remains the same, 7 minus x cubed, and all of this minus the second part, where this time u remains the same, and v is the one that's differentiated. Sorry, I just got distracted from something. And all of it is over the square of the denominator, which in this case is really just over 7 minus x cubed squared. Simplifying, I'm going to try to rub this out. we'll be left with a minus 3x to the 4 minus a 42x over our denominator 7 minus x cubed squared. And that's your final answer. Let's try one more question. For this question, we're going to go for the fourth derivative. Not just the second, not the third, but the fourth derivative. Let's go for the fourth derivative of another trig problem. But, what should we do? Let's do logarithms. We need to add some variety. We have y equals e to the minus 5 z plus 8 log 2z to the 4. Or 2z to the 4, yeah. Our first derivative will go like this. Wait, 1 second. Yeah. Minus 5 comes down, and the indices stays the same. Plus, here's where it gets tricky now with the log. Let's keep the 8. Differentiate what's inside the bracket into 8z cubed. And of course, multiply by 1 over whatever was inside the brackets. That's how we deal with logs. 2z to the 4. 1 over 2z to the 4. So y prime can just be simply stated as minus 5e to the minus 5z plus 32z to the minus 2. Sorry, minus 1. Y prime can be differentiated again for the second derivative. And you can just go by I and see that you get a 25 at the front when you bring down the minus 5 and multiply it together by itself. Indices stays the same. You get a minus 32 to the minus 2. For the third derivative, you can use I again. This is going to be my minus 125 e to the minus 5z plus 64 z to the minus 3. And you can keep on going until you end up with a constant, and that constant just differentiates to 0 really. But the fantastic thing about this problem is that won't necessarily be the case, because we have a special number here called Euler's number, Euler's constant. This guy differentiates for an infinite amount of times. So in this problem, we will get an infinite number of solutions for rates of change of other respective rates of changes before and previous, and that are their predecessors. So thank you for watching this video. It's pretty long. I know it's 50 minutes long. I've been away for a while, but like the video and subscribe if you enjoyed.